All right, so this video is going to focus on electromagnetic radiation and the characteristics that are associated with this. Light and other forms of radiation can be described in a wave-like pattern, and we can characterize these using both wavelength and frequency. The picture you have below shows as the wavelength increases, your frequency is going to decrease. So it's an inverse relationship, and you can see that your radio waves are the longer waves, while your gamma rays are your much shorter waves. So how we can relate these to one another, the whole pattern that a light or a form of radiation follows, basically going through the sine portion, or sorry, the cosine portion of your graph, thank you. That would be your wavelength. So the distance between two peaks or two troughs in your wave. The frequency is telling us how many of those waves can move through a given point in space per second. And then we can relate those to one another. If you were going to graph wavelengths versus frequencies, you would get the slope would be if you were going to graph, if you're going to show a relationship between wavelength and frequency, you would get the speed of light as your slope, 3 times 10 to the 8th. So another way you can look at it is with one of those triangles where you can have frequency equal to c over your wavelength. You can have wavelength equal to c over your frequency. I do want to point out that you also will see frequency in hertz. That is, which you tend to hear with the radio stations when they refer to AMs or FMs. And that's just talking about the unit of seconds to the -1. And so there's another picture showing you a relationship between wavelength and frequency, and basically the approximate size of those wavelengths. And then when the temperatures, you are most likely to find the most intense wavelength emitted for those different aspects of those different forms of radiation. So we have here that an FM radio station broadcasts at 99.5 megahertz. Calculate the wavelength of the corresponding radio waves. So if we want to calculate wavelength and we're being given a frequency, we can relate them using the equation we just talked about. But your hertz have to be per second, not megahertz. So we're going to have to do a conversion to get the megahertz into hertz. What I just put up before I talked about that was that I would have to rearrange that equation to solve for wavelength. Frequency and wavelength would switch sides. And so speed of light is 3 times 10 to the 8th meters per second. 1 megahertz would be the equivalent of 1 million hertz. So if I convert megahertz to hertz, I would get that that would be 99.5 times 10 to the 6th hertz, or seconds to the -1. I'm writing it in the form of 1 over seconds so that you can see how the units cancel out. And when you do the math through, you get that the wavelength is 3.02 meters. Remember again that radio waves are going to be pretty long. So at the end of the 19th century, matter and energy were considered to be separate entities. Matter was particles, and energy was in the form of waves, and they were totally separate from one another. And so various scientists came along that kind of helped to blur that relationship between mass and energy. So the first scientist that we're going to look at, his contribution, Planck, was that energy is quantized. That you would need specific inputs of energy or specific outputs of energy for electrons to move between energy levels. And so we can relate those amounts of energy that would be needed using his constant, h, 6.626 times 10 to the -34th joules to seconds. And we can use that constant to relate energy to frequency and to wavelength. So you can see there that that equation is like the one you just saw, um, with frequency being equal to c over the wavelength. We're just going to multiply those by the Planck's constant, and either one of those would be able to be set equal to the change in energy. So again, you can have one of those triangles as well. You're only ever going to be solving for delta E or the wavelength because H and C are both constants. So next scientist that we're going to look at that contributed to the blurring of the lines between mass and energy was Einstein. Einstein said that energy has mass, that you could look at radiation as being a stream of particles, aka photons, E equals mc squared. And because energy is typically going to be reported in joules, your mass would need to be in kilograms to make that metric unit, and then your speed of light would be squared, meters squared over seconds squared. So if we can look at mass being related to energy, and we can look at energy being related to wavelength, there should be a relationship between mass and wavelength. And you can see de Broglie's work using the relationship between energy and wavelength, and the relationship between energy and mass, to connect those two ideas together. And that wavelength would be equal to Planck's constant over the mass in kilograms times the speed at which those particles are traveling, the photons are traveling, the velocity. And so with that information in mind, we can relate wavelength now to mass or to velocity. And so some additional support for this idea where the lines were blurred was with diffraction. Diffraction is how we determined that you have every element has a unique number of protons. So it's when light is scattered from an irregular array of points or lines. And when we have our atoms or ions X-rayed, we see these different diffraction patterns. And the patterns themselves can only be explained through waves. So therefore, matter doesn't just have properties of particles, it's also going to have properties of waves. So here's another picture showing you that relationship with the diffraction patterns. X-rays were taken of the salt crystal, and then where the waves are in phase together, we see brighter spots on the detector screen. And then when they are not in phase, when the trials and the peaks are connecting together from the two, you would have darker spots. You would have decreased intensity. All right, so if we can say that mass has properties of waves and particles, we can also say that about radiation. We know that we can relate energy to wavelength, and from de Broglie we can relate mass to wavelength. So these are the same equations we've already talked about, showing you that you can have radiation exist in the form of waves and in the form of photons. So we're just looking at it from both sides. So just a fair amount of justification to show that that relationship isn't just coming from mass and isn't just coming from energy, that the two are going to work hand in hand with one another. So some example problems we're going to work through right now. A photon of ultraviolet light possesses enough energy to mutate a strand of human DNA. What is the energy of a single UV photon and a mole of UV photons that have a wavelength of 25 nanometers? Well, if we know our wavelength and we want to find our energy, we've already seen that there was a relationship between energy and wavelength, that delta E is equal to hc over wavelength. We need to have our wavelength be in meters. Again, there are 10 to the 9th nanometers for every meter. So there's our constants, and we're going to convert that wavelength into meters. We see that the meters and the seconds cancel, leaving us with joules, and that gives us the amount of energy per photon, 8.0 times 10 to the negative 18th. So this equation is going to be dealing with individual particles, whether they be photons, whether they be electrons. If we want to know what the energy is for a mole of photons, we're going to have to relate that using Avogadro's number, that there are 6.02 times 10 to the 23rd photons for every mole of photons. The photons would cancel out, and when we do our math, we see that we get 4.8 times 10 to the 6 joules per mole of photons. So again, using just your straight equation relating energy to wavelength, that's going to be per individual particle. If you want to know per mole of particles, you're going to have to use Avogadro's number to create that relationship. So in this next example, we have 208.4 kilojoules of energy is going to be needed to remove 1 mole of electrons from an atom on the surface of rubidium metal. How much energy does it take to remove a single electron from an atom on the surface of solid rubidium? And what wavelength, what's the maximum wavelength of light capable of doing this? Well, the energy that we were given is per mole of removing, for 1 mole of electrons being removed. And we want to know what it would be for a single electron. So we're going to take that 208.4 kilojoules per mole, and we're going to convert it per electron using Avogadro's number, that there are 6.02 times 10 to the 23rd electrons for every 1 mole. And so the amount of energy that would be needed would be 3.462 times 10 to the negative 22nd kilojoules. If we want to know the wavelength that's capable to remove a single electron, we would then be able to use our relationship between wavelength and energy to calculate that. Remember that Planck's constant is in joules, so we're going to need to convert our energy change into joules by taking kilojoules and multiplying it by 1,000. So wavelength would be equal to hc over that energy change. H is your constant, H is Planck's constant, C is your speed of light, and then your delta E would be per electron, so that's why we're using the 3.462 times 10 to the negative 19th joules. The joules and the seconds cancel, and we're left with meters. And when you do your math, you get 5.742 times 10 to the negative 7th meters. And you're often going to see me convert the wavelengths into nanometers because that's where our visible spectrum falls, around 400 to 700 nanometers. And so if it's anywhere in that range, this would be able to be done using light that we can visibly see. And so our next example is using de Broglie's relationship. Neutron diffraction is used when determining structures of molecules. Calculate the velocity of a neutron that has a wavelength of 75 picometers. So if we want to find velocity and we know wavelength, we're going to need to use de Broglie's relationship, h over m times v. We know that we want to find velocity, so if we rearrange this equation, we would get that it is equal to h over m times your wavelength. We know what Planck's constant is, and we know that a joule is kilograms meters squared per second squared. And since Planck's constant is joules times seconds, if we were going to write that using the individual units, our H would be 6.626 times 10 to the negative 34th kilograms times meters squared per second. So remember again, your mass needs to be in kilograms, and this is part of why, because of that unit for H. We're going to take our mass of our neutron, and if I was going to ask you to do a problem like this normally, I would have given you the mass of a neutron or a proton or an electron. I do not expect you to know those numbers straight out. And you are given that you have 75 picometers, which is there are 10 to the 12th picometers for every 1 meter. So when we do our conversion, we get 7.5 times 10 to the negative 11th meters. Our kilograms cancel, one of our meters cancels, and we're left with meters per second. We do the math through, and we get that our velocity would be around 5,300 meters per second.